So it is difficult to design, and it is also challenging to design any circuit with to provide them a different clock zone. But we can do if we can have a circuit like if we can do a proper sectioning and beneath the substrate, if we can give them a supply, then this can be possible for any quantum circuit. Now the cells are to be clocked with different zones, uh, and hence the circuit realization is bit difficult as far as the quantum circuits are concerned. So for the solution is only one, that physical realization of the quantum circuit is only possible if we can adopt a 2DW clocking scheme. Here, the digital cross connect system is a part of circuit switch networking arrangement that can be used for telecommunication switching, as we are designing this particular digital cross connect switch for for routing the data. Now, the motivation of the research work is to study the system, to designing the digital cross connect switch architecture, and definitely with using the quantum cellular automata software. Now here it is a very interesting part that whatever we have designed, we are designing using a silicon on chip technology, and crossbar switch modules have been designed on the integrated circuit. Now these all circuits are incorporating the crossbar schedulers also for proper routing of the data. Here also I am interested to present, I would like to present a scheduler circuit also uh, using the quantum dot cellular automata, the quantum circuit, but with a physical possibility of providing them the various clocks. Now the routing can be done efficiently to avoid the congestion or the blocking of the networks. So that's why I have taken the topic as a N cross N multi-stage switch network, because a Clos network is a multi-stage network, and that uh, to a very extent it is just stopping the blocking of the network, and the data propagation is very easy for the part. Now the routing of the data can be done efficiently for avoiding the congestion and also the blocking between the users. Whenever there is a blocking, the data routing path can be disturbed, and which is not acceptable at all. So with the advancement of the technology, electron-based circuits are also being designed so as to design the cross-connect switches along with the crossbar scheduler. So effective designing is only when we are designing the digital cross-connect switch, it's okay. But if we are not including the crossbar scheduler, there is no worth of designing such cross-connect switch if we are not giving them a proper particular scheduler architecture, or we are not designing a scheduler algorithm for that routing. So to start with the digital cross connect switch element design, I will just first of all consider a 2 switch element, and then using this switch element, I will go to the designing of multi-stage cross switch matrix, and of course some other parts which I told, that a crossbar scheduler is also necessary for routing any data, because if there is no scheduler, then there is no use of designing a switch matrix architecture, because all the switches are working when there is a proper scheduler, so that blocking can be avoided. And and here we are designing all the circuits as using the quantum technology only. So the design as shown is presenting a 2x2 basic switch element. In this, I have used a 3 input majority gate, and the gate is also, if it is -1 polarity, then it is working as an AND gate, and if it is given a polarity of 1, then it is working as OR gate. So here this is a particular 2x2 basic switch element design in which we have two users at input part and two users at the output part. So here x1 and x2 are the two users, whereas out1 and out2 are the two outputs. So it's a total 2x2 switch matrix. So this I have designed so that minimum area is required and minimum of power dissipation can be done for the given circuit design. This is the 2x2 basic switch element output, which is which can be seen from the figure. The output has been verified, obviously. Now here I have compared this circuit with a IEEE transaction paper given by Ali Bahar et al. So this is my proposed 2x2 switch element switch architecture, where I have designed with the 59 cell count, and whereas the IEEE transaction paper has designed the cell count of 72. So the cell count has significantly been reduced in the work. So we can see by proper utilization and proper designing of any quantum circuit, we can reduce the number of cells which we are using for designing of the circuit. Now here we coming to the area. So this area is 0.457 micrometer squares for 2x2 switch element, whereas it was much larger in the case of the IEEE transaction paper, from which I have compared. So if I talk of delays has also been reduced. Number of majority gates I have compromised, and inverters also. So number of crossings are also less in the presented design. So the basic aim is to understand how we can reduce all these parameters significantly with the proper selection of the designing and the proper orientation of the cells. Here, the proposed 2x2 switching module, which has been proposed, now it can be utilized for designing the 4x4 Clos network, and design can be extended for more number of input-output switching networks. So here, from using this particular 2x2 switching module, we will extend the designing up to 4x4 Clos network. Here it is worthwhile to note that this Clos network is a multi-stage network where I am trying to reduce the locking of the network, right? So here the design presented in the figure, it is employing the 2x2 switch element architecture, right? There are 2x2 SEs which I have presented here, the same SEs which has been shown here. Now I have taken these 4 modules of these SEs 2x2. So in this Clos network, this is a multi-stage network. The first stage is this and the second stage is this. So this particular architecture is employing 4 2x2 switch elements, 2 into 2, 2 into 2, 2 into 2 and 2 into 2. That means the whole designing is 4 inputs here and 4 outputs here. This particular is making 4x4. Now this 4x4 can be extended to 8x8, and then that 8x8 can be extended to 16x16 and so on. And we can design in the power of 2. The number of users can be increased at the input and output both sides. The output for the 4x4 multi-stage switch has been shown in this figure. So here we can see the output is sharp, and we have verified the output also. Now, a basic idea is the earlier circuit which has been presented was employing a 3-input majority gate. Now, if quantum circuit can work for 3 input, it can also be used as a 5-input majority gate. That means we can design the 2x2 switch module using 5-input majority gates also. So not only one design is possible, but number of designs are possible if we are employing a 5-input majority gate. So here two approaches are being presented for the designing of these 2x2 switching element, which can be further increased to obviously for 4x4 and 8x8 and so on. So two approaches are being designed. The approach 1 we will discuss, and then we will see the approach 2 designing using 5-input majority gate. So here this design is employing so much of less number of quantum cell, as we can see from the diagram. So here very less numbers of cells have been designing. So if we can see this, these is -1 and 1 polarity, out 1, B and A, and 1 select line. That means we are having 2 inputs and 2 outputs, but we are using a 5-input majority gate in the circuit. And the idea is same as the 3-input majority gate, but it is employing 2 more inputs. That means 1 and -1, both polarity have been given for designing this approach 1. So it is all about the orientation of the quantum cell for designing this particular circuit. So the result has been obtained as before, and this circuit is also working very accurately for the 2x2 switch module. Again, this particular design is again for designing of the 2x2 switch matrix, the SE element which we have discussed earlier. So here also the the orientation of cells is different, but yes, the output is again the per majority gate, and we are getting the output correctly. The A and B are the number of user at the input side, and out 1 and out 2 are the number of users at the output side, and both the polarity 1 and -1 has been given to the each majority gate, and constituting the 5 inputs to the circuit, and we are getting the output again correctly for approach 1 and approach 2. As we can see, the outputs have been verified for both the approaches, and these approaches can be extended to 7-input majority gate, or we can say by using some manipulation. For of course, why we are increasing the number of inputs. Now the question is that why we are increasing the number of inputs, whereas the circuit is working. It's a difference that here the number of cells can be reduced, as we can see from this particular table. So here all three designs have been compared, as we can see. The 5-input majority gate approach 1, 5-input majority gate approach 2, and 3-input majority gate use this 2x2 switch matrix. That means we have discussed 2x2 switch, digital cross connect switch using 3-input majority gate, 5-input majority gate approach 1, and 5-input majority gate approach 2. So the cell count in the case of 3-input, whereas we have less number of inputs, but the cell count is greater, as well as the area in nanometer square is also greater, as we can see from the table. But if we use a 5-input majority gate, whether it's a approach 1 or it's approach 2, we are getting the cell count as reduced by 10 cells we can reduce by, and hence if we are in decreasing the number of quantum cells, that means we are decreasing the area. So decreasing the area is main objective for designing any quantum circuit. Also, along with the decreased power dissipation too. So here area and cell count can be reduced, and this is about the paper which has been compared. But here if I talk of these three circuits, so we can see the 5 input majority gates are occupying very much less area in comparison to the 3 input majority gate. So all the three structures are the 2x2 switch element, but of course they are employing the less number of the quantum cells. Now if we are employing any digital cross connect switch using the uh, you at the router, then there would be some sort of calculation also. And here it's important to designing a low power multiplicative accumulation circuit. So here let us come to this accumulation circuit, where I have designed a sum and a carry circuit, a full adder design using QCA, and this recurring circuit with very less number of area and very less number of cells, we can design a MAC architecture also. Here this is the MAC architecture, where n is the number of iteration, and this is the yn is depending on the previous output, and it is also the multiplication of a into b, and which can be added. So it is a recurring. If we are taking ns2, then it will take the previous output at y1. So present output is depending on the past outputs. So in this way we can design a multiply accumulate circuit also. Let us see the simulation result and some observation about the MAC circuit. So total area is coming out to be this per figure, and that is 1,84,086.53 into 10 raised to the power 2, and this energy dissipation is very less, and power dissipation is also very less for the MAC circuit. Now coming to the crossbar switch scheduler. So earlier I was presenting and talking about the 2x2 switch architecture with the 2x2 switch architecture for designing the digital cross connect switch. Now I am discussing the crossbar scheduler for the system Verilog. And I will compare it with the system Verilog and the quantum dot cellular automata. That means now I am going to present two-dimensional crossbar switch scheduler, and also I will compare the crossbar scheduler designed with QCA and the same crossbar scheduler designed with the system Verilog. So we will see the power dissipation in both of the circuits, and also I am going to present a physical realization for the quantum computing. Now this is a crossbar scheduler in which is following a particular algorithm. Let's say if I am having a 3 cross 3, that means I have 9 cells, and all the cells are connecting from input to output, and these are the input side and this is the output side, and here it is an intermediate state. So whenever this particular block is active, there would be no block active in the same column or in the same row. This is the particular algorithm. And if this particular block is active, then there would be no block active in the this same column or same row. So the data propagation will be diagonal. But here the diagonal circuit are not connected, so they are not going to interfere each other at all, and hence this particular is responsible for connecting one to one user, and this particular is connecting from two to two user, and this particular is connecting from 3 to 3 user. That means And if this particular block is active, then data propagation would be from the second user to the third user at the output side. So this is a particular crossbar scheduler which is working at a definite algorithm. So this crossbar scheduler, since we have already proved that QCA technology is always looking good in comparison to the CMOS technology. So why not to compare this crossbar scheduler with Verilog, system Verilog. So the same crossbar scheduler, a single cell, a single scheduler cell is being compared with the system Verilog. Here, this crossbar scheduler is presenting the is presented using QCA technology, and this crossbar scheduler is presenting the circuit using the system Verilog. Again, the design, this particular design has been increased to 3 cross 3 scheduler. That means this is a particular 2 cross 2, 2 cross 2, and now I have increased up to three users at the input side and 3 users at the output side. And thus this particular complete system, this figure is representing the design using quantum dot, and this particular figure is presenting the design using system Verilog. Now the assessment criteria would be the power dissipation by the both the technologies. So proposed on chip scheduler using CMOS technology, it is consuming the power of 81 milliwatts, whereas in the case of quantum dot cellular automata, the power would be very less in comparison to 81 milliwatt. It is just 88.8 into 10 raised to the power minus 6 milliwatts. So the technology of quantum dot is far better than the technology for the CMOS uh, for if this particular algorithm is working. So we can extend so many algorithm and so many algorithms I am working on, so that I would be able to give a perfect solution for scheduling the data from input to output side. Now the basic problem with the quantum circuit is to provide the clock zones to the circuit. This is a basic problem with the quantum circuits. Now I think there can be a solution if we make a section of zones, and each zone is providing the same clock to the number of cells occurring in that particular zone. So if I divide the circuit in these clock zone as shown in the figure, so this particular, if it is all the cells coming here, all the cells can be clocked by one clock zone. This particular these cells in this zone can be clocked by a different clock zone, and this gray area can, all the cells coming in this gray area can be clocked by a single clock zone. Then that means whatever 4 zones which we are giving, then we can obviously, this using this TW clocking scheme, we can definitely give the clocking to the designed circuit successfully, and there is no problem in designing the quantum circuits at physical realization. So this is also this data has also been verified, and the circuit is almost giving the same result if we if they divide the circuit in various clock zones, and all the cells coming in a particular clock zone can be clocked with the same clock pulse. Of course, there is a concept in quantum computing for the reversible circuits also, and all the reversible circuit can be designed, all the latches and combinational circuits can be designed for using the reversible logic. And here, so digital switch architecture can also be designed for using the reversible logic circuits. So here the basic idea uh, was to improve the reversible gates. And as we know, there are so many reversible gate, Feynman gate, Fredkin gate, and Paris gate, whatever it is. So we are designing the from to starting from so many years ago. Now we are in the era that we have designed so many reversible circuits using these reversible logic concept in case of the quantum computing uh, field. So the gate, all the latches have been designed and compared, and the QC performance of the QC simulation has also been presented, and number of cells are being given here in the table. Now the basic idea is how to design and what should be the algorithm for designing reversible logic circuit. So I have developed an algorithm for designing the reversible logic circuit. Let us define all the input and output equations for the selected reversible gate, and then we can derive the equations for the realization of the required circuit. That means first of all, we have to define all the inputs and outputs equations, whatever reversible circuit we are going to design, derivation of the equations, and then for establishment of reversibility, we have to calculate the number of garbage outputs which we are going to provide them. And those garbage outputs should be aligned with the inputs of the inputs, and then only the selected reversible gate can be designed and can work perfectly. Now once the design part is okay, we can simulate the defined equation in terms of majority gates, and the once the majority gate design is over, we can design the circuit on quantum.cellular automata. So here I am giving just some idea for designing the latches using these various reversible logic gates. The SR latch using 4 Feynman gate. Here JK latch has also been presented using 4 Feynman gate. D latch I have designed only using Feynman gate D latch, and we can have uh, the the proposed circuit which the earlier work. So here D latch using Fredkin gate and D latch using Fredkin gate was using the cell count of 575 and 292, whereas the proposed D latch using Feynman gate, which I have realized it is using only 287 number of cells. Similarly, the proposed T latch is using Feynman gate is better. So that we can see, if we are changing the gate, reversible gate, and the same circuit is being designed, we can also decrease the number of cells, and the clock cycles can also be decreased to the significant time. So here JK latch using Fredkin gate and JK latch using Feynman gate is only using 171 number of cells, whereas the JK latch using Fredkin gate is using 780 number of cells. So this comparison is quite visible, that if we are using Feynman gate to design a proposed JK latch, then obviously it is it is employing very less number of quantum cells. Similarly, in case of SR latch, the SR latch using the same Fredkin gate, it is using 1149 number of cells, whereas SR latch using Fredkin gate is using 981. But if we design the same SR latch using Feynman gate, we are reducing the cell count to from 1149 and 981 to 165, and obviously we can see the clock cycles can also be reduced from 3 to 0.5. So here now the future scope. The 2x2 switch matrix can be extended to design as we have designed for the Clos networks. We can also design the circuit for the beams networks also, and so many rearrangeable networks are also available, and we can have these networks designing using quantum dot obviously, and the 2x2 switch basic unit can be used for designing these all rearrangeable networks. It has that much of flexibility that this 2x2 switch module can be used to increase number of users, and it can also be employed to increase so many other circuits also, which which are available, and especially for the multi-stage networks. So all the architectures can be extended to 2 DW clocking scheme, where this 2 DW clocking scheme is very important, because the main problem for realizing any quantum circuit is to give the proper clock zone, which is always not possible. But if we employ this particular technique, we can give a proper clock zone, and we can get the desired output also. So here now the various combinational logical circuit can be designed, and in future as I have found out that this if we are getting the number reduced using various reversible gate for the same design, if we are able to employ other gates also, then the latches can also be the number of cells can also be reduced, as well as the area can also be reduced. So these are the references. Any question? If anyone asks, the most that is most welcome. Please ask if any doubt is there.
It looks like no doubts. No? Participants, any queries? Seems like everything is clear, ma.
Okay, so thank you for listening.
Just a second, I'll ask Preeta Sharan, ma. Participants, please turn on the camera. For 2 minutes, we'll take the group photo. Thank you all. Okay, thank you, everyone. On behalf of Oxford College of Engineering, I would like to express my deep sense of gratitude to Dr. AmitaAsthana ma'am for accepting our request and delivering an excellent session on end-to-end digital cross-connect switch using quantum dot cellular automata. And it was really informative session, ma'am. We have received so many messages from the participants that it was very useful. Thank you so much for joining us today, ma'am. Thanks a lot.
Thank you so much. Thanks to you all.
And thanks to all the participants for joining the session and giving your continuous feedback. Thank you all. Thank you, ma'am. We'll share the session feedback now in chat box as well as in a WhatsApp group. Yeah, link is posted. Please give your feedback for both our morning and afternoon session. Thank you, everyone. We'll see you on Saturday morning. Tomorrow, there will not be any sessions. So we'll meet you on Saturday morning.